So here's example 2 of our inclined planes example. So in this example, we'll be given the diagram this time. In the first question we weren't, but we're given the diagram. Diagram shows a box of mass 2 kilograms being pushed up a smooth plane. So again, it's smooth, so we don't need to worry about friction in this example. It's being pushed up a smooth plane by this force of magnitude 2 newtons. So although that force is not parallel to the plane, the result of that force acting that way is that this 2 kilogram box starts moving up the plane, starts accelerating up the plane, okay? The plane is inclined at an angle alpha, where tan alpha is 3/4. Now this is interesting in these questions because we could use our calculator, obviously, to do inverse tan and find the value of alpha, but actually because this is given as a fraction, we can have a little look here at a right angle triangle and say, well, okay, so tan is opposite over adjacent, and using Pythagoras, that's going to give me my hypotenuse as 5. So that means that tan alpha is 3/4, sine alpha, opposite over hypotenuse, 3/5, and cos alpha, adjacent over hypotenuse, 4/5. And that's quite useful sometimes to have these nice exact values going into our calculations for sine theta and cos theta when we're looking at resolved forces. The first thing I'm going to do here, actually, I'm going to redraw this diagram before I start answering these questions. And the reason I'm doing that is because this 2 newtons here looks like it's just sort of floating in midair. You know, the point of action of this force is just over here somewhere. So it's going to be reasonably difficult to get our components of forces on our diagram when we're not actually quite sure what's happening here. But the result of this force acting this way is exactly the same. You know, if I'm pushing this box, if I'm pushing the box this way, that's exactly the same as if I was pulling the box from the inside with a force of 2 newtons. So the fact that this 20 newtons, the fact that this 20 newtons is pushing here would be exactly the same as if the force was acting at the body and pulling it 20 newtons in this direction. And I'm going to redraw that there just so that all of my forces are actually acting from this box, and my point that starts here with my arrows is going to be on this box. So that's what I'm going to do. First of all, I'm going to redraw that diagram out. So let's redraw this. So here's my angle alpha, where I've got tan, sine, and cos alpha from over here. So that's my angle alpha. I've got my box on here. And this time, my 20 newtons, I'm going to redraw that, as I say. So I'm going to redraw that so it's acting actually on that box there. Okay, so there's my 20 newtons, just redrawn from there to there. It's got the same result there. My mass of 2 kilograms, so I'm going to put that on my diagram. Acting downwards. So we've got a weight of 2g. And it's being pushed up the box, so my resultant acceleration, my resultant motion is going up the box. I'm just going to put that on my diagram to remind me that that's the way that this thing is actually moving. So here's my box here, and there's my forces that are happening. The other one I want to put on is my reaction force there. And then we're asked to find the reaction force, and we're asked to find the acceleration of this box. Okay, so again, we're going to look parallel and perpendicular to this line of motion, to this plane. So I'm going to have to split these forces up into their components. Let's do the 20 newtons first of all. So the 20 newtons is acting in this direction. So I've got a component there of my 20 newtons that way, and another perpendicular component that way, so parallel and perpendicular to the slope. And so this force, if this is alpha, then this angle is alpha as well. Corresponding angles on parallel lines there. So this now is going to be my 20 cos alpha, and this is going to be my 20 sine alpha. Okay. My 2g then, if I split this up now into parallel and perpendicular, so I'm going to have quite a few forces on my diagram here. So if I split this one up into parallel and perpendicular, Then, if this is alpha, then this is 90 minus alpha. I don't really want to get into using 90 minus alpha. So if this is 90 minus alpha, this one is alpha. So there's my angle alpha there. So this is 2g cos alpha, and this is 2g sine alpha. And it's important that your diagrams aren't too small. You know, some of you in class have had a habit of drawing quite small diagrams. Make sure that your diagrams are big enough that you can see all of these different components of forces on here. So now when I'm looking at my resultant force equations, my equations of motion, parallel to the plane, I can now ignore this 20 newtons because I've replaced it by these two components, and I can ignore this 2g because I've replaced it by these two components. Okay, so let's have a look at perpendicular to the slope first of all. I'm just going to move this up so that you can see my working when I start working down here. So let's just move that question up. Okay, so perpendicular to the slope, perpendicular slope, and I'm going to take that way as positive. So let's have a look at that equation. So perpendicular to the slope, we've got r acting in the positive direction, and then in the negative direction, if that way is positive and these are both acting in the opposite direction, I've got minus 2g cos alpha and minus 20 sine alpha. So that's my resultant force. There's nothing happening this way. There's no motion this way. Perpendicular, so that resultant force is going to be 0. And now what I can do, I can substitute in my cos alpha, if you remember, was 4/5. My sine alpha was 2/5. So that was 4/5, and then 20. My sine alpha, sorry, was 3/5, should I say. That equals to 0. If you carry on with this, rearrange it, you should end up, please do that. So you'll end up with 27.7 newtons to 3SF. Okay? And it doesn't matter which order we do these in. I've done perpendicular to the slope there. I'm now going to do parallel to the slope. And here as well, I should have probably said my resultant force is 0. Parallel to the slope, so this one, my resultant force isn't 0 because there's some acceleration up the slope, so my resultant force is going to be ma. So parallel to the slope, this time the motion is up the slope, so I'm going to take up the slope as positive. If you remember in that last example that we did, we took down the slope as positive because the thing was sliding down the slope. So I'm taking up the slope as positive. Let's have a look at this then. And if there was friction here, if it's smooth, this one again, if it was rough, then we'd have some friction pulling this thing back, and the motion pushing upwards would be pulled back by some friction, but it isn't. The only thing that's pulling it back is the component of the weight. So let's have a look. Parallel to the slope, positive direction, 20 cos alpha, negative direction, 2g sine alpha, and that's my resultant force, which is equal to ma. Mass is 2, so that's equal to 2a. Substituting in for cos alpha 4/5, and for sine alpha, 3/5. Playing around with that, again, I'll let you do that. You should end up with your acceleration, write out your fuller answer, and then if I round to 3SF, we should get 2.12 meters per second squared. And there's our two questions answered. The normal reaction, 27.7, the acceleration, 2.12. Again, I'm going to stop the video. I'd like you to get this into your notes, and then we'll look at one more example with pulleys, which are acting over an inclined plane, and then I'll give you some questions to do yourselves.